Okay, so hi everyone. This is the sixth uh, lecture in this fluid and particle mechanics course. So, in this sixth week, uh, professor went through the particular problem of sedimentations and separations, where he discussed about the different regimes of settling and the differential settling and the settling of colloidal particles, where the uh, electrostatic van der Waals and the electrical double layer forces are acting on the particles, and because of those interparticle forces, how the particles aggregate while they are settling. Okay, so but uh, in this live session we will mostly talk about the the problems which were given to you, particularly the assignment 6. Okay, so I will try to solve few of these questions, and then if you have any confusion you can ask me. Okay, so uh, in this, so let me go to that assignment problems. Okay, so I'll start with the uh, question number. I'll pick it as question number 1. Okay, pick it as question 1. Okay, so what it says, that consider a spherical particle of diameter dp. So let me draw a spherical particle. So I have a spherical particle of diameter dp, okay, of mass m, moving through a fluid in one dimension under the action of gravity. So you have the gravitational force acting on the particle. Okay, particle have the diameter dp, okay, mass m, and it's moving through a quiescent fluid under the action of gravity, okay, with a constant velocity u. So the velocity of the particle is constant, which is small u. Okay, assume the density of the fluid to be rho. So the density of the surrounding fluid is rho, and that of the particle is rho p. So the density of the particle is density of the particles is rho p. Okay, so the particles is characterized by diameter dp, mass m, and density rho p, and the fluid is characterized by density rho and dynamic viscosity mu. Okay, so this is my problem. So I have a fluid body, or a large tall container, you can think of in that way, and I have a small particle of diameter dp, mass m, and density rho p, where the fluid has density rho and dynamic viscosity mu, and the g is the acceleration due to gravity. Okay, so this is how it looks like. Okay, so then before going into the details of the problem, let me see what are the different forces acting on the particle. Okay, so I will draw it again. I will draw the free body diagram of the particle. Okay, so here I have the particle. This is my spherical particle. Okay, I'll just characterize the different quantities of this particle. So let me write it down. diameter of the particle is equal to capital D dp. Sorry, that means the radius of the particle AP is equal to dp by 2. It's very simple. Now the mass of the particle is m. Density of the particle is equal to rho p. Okay, density of the fluid is equal to rho, and dynamic viscosity of the fluid is equal to mu. Okay, now so what are the different forces which is acting on the particle? Can someone tell me what are the different forces that acting on the particle? So let me draw the free body diagram of the particle. Okay, so I will draw free body diagram of the particle. Fine. So that means I am trying to say what are the different forces which are acting on the particles. So let me draw it here. So this is my spherical particle. What are the different forces? It is settling due to gravity. Okay, that means you will have the gravitational force. Let's say I will call it as Fg. Okay, then you have the density difference between the fluid and the particles. So when you have the density difference, there will be a buoyancy force which will try to resist the motion. Okay, or which will act in the direction opposite to the velocity. So you will have the buoyancy force which is acting upward. Okay, I will call it as Fb. Okay, and there is other force. Okay, when the particle move through the fluid, the particles will experience a drag force because of the fluid. Okay, and this drag force will also act opposite to the motion of the particle. So I will call it as Fd. Okay, so what are the different forces? And let's say my particle is settling with a velocity u and it has some acceleration. Let's say I will call these accelerations as a. Okay, so from the Newton's second law of motion, okay, what is the equation of motion for this spherical particle settling under gravity in a quiescent fluid? So the equation of motion for this will be m into du by dt. So what is m du by dt? Is the acceleration. Okay, so du by dt is the acceleration, m du by dt is the net force acting on the particle. What is that net force acting on the particle? It is Fg, the force due to gravity, minus the buoyancy force minus the drag force. Okay, so this is your basic fundamental governing equation, okay, for the motion of the particles which is settling through a quiescent fluid under the action of gravity. Now I have to quantify what are the different forces. Okay, so what is the external forces here in this problem? The external forces is, the external force acting on the particles is the gravity. Okay, so let me write it down. The gravitational force acting on the particle Fg is simply mass time acceleration due to gravity, m into g. Now the buoyancy force acting on the particle Fb is equal to the immersed volume of the particle, which is, what is the immersed volume of the particle? What is the volume of the particle? Volume of the particles is m by rho p. So m is the mass of the particle and rho p is the density. So this is the volume of the particle. The d times the displaced mass of the fluid times rho into acceleration due to gravity. Okay, so this is equals to m rho g divided by rho p. Okay, so this is the buoyancy force which is experienced by the particle because of the density difference, because of the density difference between the fluid and the particle. Here the particle density is more, that's why it's settling downward under the action of gravity. And the last quantity, which is the drag force on the particle, which is very important. Drag force acting on the particle Fd is equal to, you know from the Stokes drag formula, that from the Stokes drag formula it is 6 pi mu u into radius of the particle, which is AP. If I write it in terms of the diameter, it is 3 pi mu u into dp. So this Fd is called Stokes drag. Okay, so when the particle will move through in the quiescent fluid, it will experience some resistance because of its motion, which is called the drag force. Okay, and one can derive this expression for the drag force from the fundamental low Reynolds number flow problems, where you have to calculate the velocity field, the disturbance velocity field created because of the particles motion of the fluid, and then you have to use the constitutive equations for stress experienced by the particles, and then integration of that trace traction along the surface of the sphere will give you the drag force which is experienced by the particle. So that requires a detailed derivation. Okay, but here we will simply use the formula. So this is equal to 6 by mu a u. So now So now I know the different forces which are acting on the particles. Okay, one is the, here the external force is the gravity, that's why the mass into acceleration. Okay, mass into acceleration due to gravity here. So other is the buoyancy force which is acting on the particles, and then the drag force which is acting on the particle. Okay, so then uh, how the equations of motion for these particles looks like. So equation of motion, which is m du by dt, you have mg minus, we have fb, that is m rho g divided by rho p minus 6 pi mu u ap. Okay, now there is the concept that when the particles will fall at constant velocity. Okay, so when the particles will fall in constant velocity, what will be the net force acting on the particle? Will be zero, because there is no accelerations of the particle. So that is called the, that is, you can think of as the particles has reached its terminal velocity, it's reached its steady state velocity. When the velocity is not changing with time, it is just falling at a constant velocity. At that time, this left hand side term, which is the inertial term, will be equal to 0. That means the particles is not experiencing any inertia. Okay, I am considering that the particles is inertialess. So there are two things, that the particles have its inertia, I am just neglecting the inertia of the particles, and the other thing is that the particles is falling at a constant velocity. So as it's moved with a constant velocity, the net accelerations is 0, therefore the net force acting on the particles is 0. So that means at terminal state, okay, when the particles will reach its terminal velocity, that time the equations of motion will look like that mg minus m rho g divided by rho p minus 6 pi mu u ap is equal to 0. As simple as that. Okay, so then if one calculate what is the u in this case, what is the terminal velocity, so I will write it as ut, terminal velocity. So what is ut? That means the 6 pi mu ut into ap is equal to, I have mg minus m rho g divided by rho p. Is this right? Fine. So then what is ut from here? Ut, terminal velocity of the particles, that means the maximum velocity it will reach when it will fall. This is the terminal velocity ut. So this is equal to 1 by 6 pi mu ap into mg into 1 minus rho by rho p. As simple as that. Okay, now I will simplify it further. Okay, so what is the mass of the particle? So mass of the particle m is equals to 4 by 3 pi radius cube into rho p, right? I'll just put that. That implies terminal velocity of the particle ut is equal to 1 by 6 by mu AP. I'll put the 4 by 3 pi AP cube rho p g into rho p minus rho divided by rho p. So what and what is cancelling out? So from here I have pi cancelling out, rho p cancelling out. Okay, so what will I have is 2 rho p minus rho g. I have AP square, okay, divided by 9 mu. Is this the correct expression? Yes. So 2 into delta rho, that is rho p minus rho, so the density of the particle minus the density of the fluid into acceleration due to gravity into radius of the particle square divided by 9 mu. That's the expression for the terminal velocity. Okay, so fine. So we have derived that what is the expression for the terminal velocity. So let me now go to that question. So I'll just box it. So this is your expression for the terminal velocity. Fine. Now let me go to the problem. Okay, so what is asked here? Okay, so the first question they asked, the force of gravity acting on the particles, it's simply mg. Okay, the force of gravity acting on the particles will be simply mg. The buoyancy force acting on the particles is this m rho g divided by rho p. It will be this, and the drag force acting on the particles will be this. So it's very simple 3 marks question. Now I will go to the question number I guess 7 and 8. Let me solve the first question number 7 and 8. Okay, so this is the question number 1. So I'll just write the question for your benefit. So this is one question. Okay, sorry. So I'll just write it down. Question 1. Question 1, the answer is mg. Question 2, the answer is m rho g divided by rho p. Question number 3 is 3 pi mu u into dp. Okay, fine. So these are the 3 answers. Now I'll go to the question number 7, another question. Question, let's say this is capital 2. What was that? It was capital 1, right? What I removed it. I removed it. Okay. So what it says, first let me read the question very carefully. It says consider a spherical particle of diameter d of mass m moving through a, it is the same wording, moving through a fluid in one direction under the action of sorry, not this a spherical particle of mass. So what is given here? The mass, a spherical particle of diameter. So you have dp is equal to 0.10 millimeter, that means 10 raised to minus 4 meter. So radius of the particle AP will be equal to 5 into 10 raised to minus 5 meter. Okay, made of steel and density rho p is equal to 7870 kg meter to the power minus 3, falls under gravity at terminal condition through a liquid of density 820 kg meter to the power minus 3 in a very large diameter tube. The viscosity of the liquid mu is equal to 10 this is millinewton second per meter square. Okay, I think there is a mistake, m will be n, I guess, so I will just consider it like that, millinewton second meter to the power minus 2. So this is actually millinewton, so it will be 10 raised to minus 2 Pascal second. Fine. So these are the data which is given to me, and then it's asking calculate the terminal velocity of the particles in SI unit. So this is how it's the data. I now quoted the data given. What it's asking? It asking the terminal velocity of the particle. So what is the terminal velocity of the particle? ut is equal to 2, I have derived the expression for ut, rho p minus rho g ap square divided by 9 mu. Okay, this is the formula. So let me put the data. What will be that? 2, what is rho p? 7870 minus 820, g is equal to 9.81 meter per second square, ap is equal to 5 into 10 raised to minus 5 whole square, right? 5 into 10 raised to minus 5 whole square divided by, you have 9 into 10 raised to minus 2. Okay, so then what will be this? Let me calculate it. If someone has the calculator, you can calculate. So it will be 8780 7870 minus 820 into 9.81 into 25. Divided by 9 is equal to this. Okay, into, I will have 10 raised to minus 8, 10 raised to minus 8. So it's coming as 0.00 0.00384 meter second inverse. Okay, is this clear? This is a very simple formula based problem. There is nothing difficulty in it. So let me go to the question once. So this is question number 7. So the answer for the question number 7 is 0.00384 meter second inverse. Okay, but the next question says calculate the Reynolds number of this fluid particle problem. So Reynolds number, you can calculate it based on the fluid velocity, okay, and the characteristic length scale of the problem, okay, and it depends on the density of the fluid and the dynamic viscosity of the fluid, or simply the kinematic viscosity of the fluid. So if I write it down, that Reynolds number, but here we will calculate the Reynolds number based on the particle diameter. So this is very much important. So Reynolds number based on the particle diameter, let me write it down very well. So the Reynolds number based on the particle diameter and the terminal settling velocity of the particle is REP, I will write it as REP is equal to, it depends on the terminal settling velocity, okay, this is UT dP rho density of the fluid divided by mu, dynamic viscosity of the fluid, as simple as that. So you have to keep in mind that here, to calculate the Reynolds number, we are calculating the Reynolds number based on what are the characteristic length scale and the characteristic velocity which are involved in the problem. So the characteristic length scale is this, the particle diameter here is the characteristic length scale. So let me write it down. So this is the characteristic length scale, and what is the characteristic velocity involved in the problem? The characteristic velocity is the terminal settling velocity, okay. So this terminal settling velocity is the characteristic velocity scale, okay. So now this is very simple. So what is REP? So this REP is equal to UT into 2AP, 2 into diameter of the particle, into rho divided by mu. Just put the values. What is UT, which we calculated just few minutes back? It is 0.00384. Am I right? 0.00384